Assalamualaikum warahmatullahi wabarakatuh. My name is SYAHMI bin HUSAINI. My metric number is DE210109. Okay, today our group will present about our group assignment, which is cement mixer speed control system. We are from group 9, section 2. Our group member is ADNAN bin Abu Bakar. Metric number is DE210067. Second one is SYAHMI bin HUSAINI. Metric number DE210109. The third one is Muhammad HARIEZ bin SAKRI. Metric number DE200085. Next, Muhammad LUQMAN bin Muhammad SAFU'AN. Metric number is DE210081. And the last one is UMMI RAIHANAH binti ROSLEE. Metric number is DE210061. For introduction, a direct current motor, sometimes known as DC motor, is an electrical machine that converts electrical energy into mechanical energy by producing a magnetic field generated by direct current. When a direct current motor is turned on, a magnetic field is formed in the stator. The magnetic fields attract and repels magnet on the rotor, causing it to revolve. PID is respectively stand for proportional integral derivative control, is the most common control algorithm used in industry and has been universally accepted in industrial control. Industrial control system and other applications that demand constantly modulate control frequently employ PID control. It is a control loop feedback mechanism. Temperature, pressure, speed, flow, and other process factors may all be controlled with PID. Proportional control produces the control output proportional to the current error. The fundamental purpose of an integral controller is also known as I controller, is to lower the system steady-state error. To obtain a good speed of response in case of a P controller and improve the steady-state response. Proportional and integral controllers are frequently combined in case of I controller. A derivative controller observes how quickly a process variable changes per unit of time and generates an input proportionate to the rate of change.
Okay, Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad HARIEZ bin SAKRI and I will continue to the literature review of our group project. So the PID controller is one of the most widely used control system in the industry due to its ease of understanding and high effectiveness. So the main advantage of the PID controller is that engineers who have a basic understanding of differentiation and integration can construct control system even if they don't have extensive knowledge of control theory. So there are three-part system in PID controller, which is the first one, the proportional compensation, second, derivative compensation, and the third, integral compensation. So beside that, there are three types of PID controller tuning methods. So the first is trial and error method. Second type of PID controller tuning method is the Ziegler-Nichols method, which is one of the most commonly used and popular methods of tuning a PID controller. So the final method is Cohen-Kuhn method, which is known for its flexibility in handling a wide range of processes. So in conclusion, the PID controllers for DC motor are used to regulate the speed of a DC motor by comparing the actual motor speed to the desired speed and making adjustment to the power supply accordingly. So that's all for literature review, and we continue to the next part. Thank you.
Hi, Assalamualaikum. My name is UMMI binti ROSLEE. My metric number is DE210061. So I will present the problem elaboration for the PID controller design. We all know that the controller is electromechanical with gear. We derive the model by a mathematical model of electric circuit first. Then we Laplace transform the armature circuit. This for question 1. For question 2, next, Laplace transform of electromechanical equation. Omega m s equal to s theta m, and Ia equal to Tm per Ke. So for the back EMS, EBS equal to KBS theta m. Then substitute equation 5 and 6 into equation 1. So 5 and 6, this one 5, 6 in equation 1. Then we get for the equation 7. Then equation of force applied to DC motor with gears. This the equation. So R1 theta M equal to R2 theta L. So we know that R1 equal to N1, R2 equal to N2. So we get the equation for equation 11, theta L equal to N1 per N2 theta M. Then substitute equation 9, 10, 11 into equation 8. Yes, step by step. Then let JL and JM N1 and 2 square equal to JT. BL plus BM N1 and 2 square equal to BT. So the equation will be like this. We simplify the equation. Then so for the final transfer function, we get theta ms equal to Ka VAS equal to S square JTLL plus S square JTRA plus BTLL LA plus S KAKBS plus BTRA. After we get the transfer function, we include the data given into the equation. So the final transfer function, we get theta ms per VAS equal to 1.28 over 0.0002387 s cubed plus 0.0221 s square plus 1.6 s. So based on equation 2 and 13, block diagram of DC motor dynamic as below. So this is our block diagram of transfer function. Okay, for the manual tuning of PID gain, we determine characteristic equation above block. Characteristic equation is 1 plus KGS HS 1.28K per cos per 0.0002387 s cubed plus 0.0221 s square plus 1.6 s. So we equal to 0. Then we use Ritz-Hurwitz method. Then by using cross multiply, we get this for A. Then B we get 1.28K. So in order give an equation a stable condition. So K we get 115.74. The second step we let K be greater than 0. So for the stable condition, K greater than 0 and less than 115.74. So critical K 115.74. So for the roots we get 81.88. Then we get PCR. Per oscillation we get 0.077 second. So this is for the PID controller gain from manual tuning 7.1. Mostly we for KP we get 57.87. For PI KP 52.083. For TI 0.0642. For KI 811.68. For PID for KP 69.444. For TI we get 0.0385. For KI we get 1803.74. For TD 0.009625. And lastly for KD for PID 0.6683. So this is the subsystem of the PID controller in MATLAB. So I will pass the presentation to Luqman.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Luqman bin Muhammad SAFU'AN and my matric number is BE30503. Question first. Based on Siemens mixer speed control system as shown by figure 1 and do the following. Derive its mathematical model and block diagram. Okay, for the second one, determine PID gain manually. Third one is create the system block diagram and manual tuning PID controller on MATLAB simulating and attach it on the report. Next, implement P, PI and PID controller using PID gain from table 1. System without controller, open loop, and plot the response, each of their response versus input signal. Okay, next, create the system block diagram for automatic fine tuning PID controller on MATLAB Simulink. Develop table for comparing the PID controller gain from manual and automatic tuning. And for the last one is plot comparison to PID controller's response input as manual versus automatic tuning. Okay, that's all. Okay, for now I will will explain about the block diagram that I have done in MATLAB. Okay, as you can see here, first of all we must run the MATLAB. Okay, then we go through the scope for the closed loop, for the open loop. Okay, so this is the response for the first one. Okay, so next we go through for the second one, which is for the P controller, this one. So we run again. Okay, and then we check the response. Okay, now this is the graph response for the P controller. As you can see here, this is for the 1500 RPM. Okay. So first thing first, we must change the final value into the 1500 because the input that we use is 1500 RPM. Okay, next for the third task is we need to find the PI controller, and we need to check the scope. Okay, so this is the graph after we run the circuit for the PI controller. Okay, and then we go through the manually PID controller, which is this one. And after we connect all the circuit, we using the 69.444 for the KP. For the I, we use 1803.74, and for the D, we use 0.6683. Okay, this is the integrator we need to integrate, and this is the derivative. Okay, after that we go through the subsystem, and then we run again, so we can get this circuit. Okay, this is the PID controller response for manually in using MATLAB. Okay, as you can see here. Okay, after that we construct the auto block diagram tuning, which is this one. Okay, we first we go to the PID. This is for the auto tune. Okay, and then we tune it. It will take for a minute, so okay, this is the response for auto tuning. Okay, and then we update then we can see the parameter for the auto tuning. As you can see here, the rush time is 4.88 seconds, setting time 17.3, so the overshoot is 7.94, peak 1.08, gain margin, phase margin, closed loop stability. Okay, after that we run it again, and we can see the response output for the automatic tuning. last one is we need to compare the manual versus the automatic tuning. Okay, as you can see here, this is the step response for manual tuning versus automatic tuning, and all the graph that we have find, we must put it in the report. So now I will continue my part.
Assalamualaikum warahmatullahi wabarakatuh. My name is ADNAN bin Abu Bakar and my matrix number is TE210067. So for the next part is the system block diagram and manual tuning for PID controller on MATLAB Simulink. So this is the block diagram and this is the graph. So next is implement P, PI and PID controller using PID gain from table 1, system without controller, open loop, and plot the response each of their response versus input signal. So we have to do the MATLAB simulation without controller first. So this is the block diagram for P, and this is the graph, and in for the KP, TI, KI, TD and KD. And for PI controller, this is the block diagram, and this is the graph, and this is the value. And for PID controller, this is the block diagram, and this is the graph. So as shown in the chart above, we can modify the tuning to be nearly identical to the input of the motor wave after implementing a PID controller with manual tuning for 1500 RPM speed motor. To obtain the values for KP, KI and KD, we use the empirical PID gain tuning method, which require a series of trial and error to obtain the correct gain to obtain the graph shown above. So the next one is for the automated tuning. So this is the block diagram and this is the graph. So this is also the automated tuning response graph that we get from MATLAB simulation. And this is the comparison between PID controller gain from manual and automated tuning in table. So from the result of manual tuning and automated tuning, we can see that there are huge difference in value for each gain, especially proportional gain and derivative gain. For proportional gain in manual tuning, it requires the value of 69 and 69.444, while in automated tuning, the value become less compared to the manual one, which is 1.703. This can be seen the slight gap at the slope comparing the manual one and automatic one. The automatic tuning has bigger gap, while the manual one has small gap comparing to the input of the motor. For integral gain KI, the comparing values are nearly the same with KP value, which is the value is 811.68, while the automatic tuning, the value is 0.611. For derivative gain KD, the value difference between manual tuning and automated tuning are huge, which is 0.6683 and negative 0.302. This can be seen in the graph, which is the manual tuning graph nearly equal to the input of the motor, while automatic tuning graph has slightly different, which includes the overshoot value. And the third one is the comparison between manual tuning and automatic tuning graph in MATLAB. So this is the graph shown in the MATLAB, and this is the value for input, manual and automatic tuning. And this is the MATLAB. So according to the comparison between the two PID controller response, which are manual tuning and automatic tuning, we can see few results which are overshot percentage, peak time, right error, condition stable. So based on the comparing graph, we can see that the overshoot value for manual tuning is less than automatic tuning. We can see the graph for automatic tuning has slight overshoot, but the overshoot value is at the maximum value, which is 51.9%. For the peak time, automatic tuning has a later time compared to the manual tuning, which is 1.52 seconds, while manual tuning peak time is 1.08 seconds. It is clear from the generated graph that automatic tuning achieves a faster rise time than manual tuning, which takes 0.0643 microsecond compared to automatic tuning's 4.88 microsecond. The gap in slope between manual and input tuning and automatic and input tuning reveals that manual tuning's rising age begins to rise before automatic tunings. Next, for the settling time, the condition need to be in between plus minus 5%. The result that we get is for manual tuning, the time settling is 17.3, while automatic tuning settling time is 1.04. For the error conditions table, we cannot get the specific value for the project, so we conclude that there is no error happen or it already stable in this while we run the PID controller system.
In conclusion, to summarize our research, the controller is designed with proportional integral derivative based on the Siemens mixer control system PID. The PID control system is critical for efficiently controlling the speed of the DC motor. The simulation result shows that the suggest PID approach solves issue much faster than the conventional algorithm. A proportional controller will lower but never completely eliminate steady state error and rising time. An internal controller will reduce the steady state inaccuracy, but the quick reaction may be exacerbated. The transient response will increase positively by increasing system stability, minimizing overshoot, and effectively reducing overshoot using a derivative control. The normalized value of the PID's output performance is extremely accurate. That's all from our group. Thank you.